A general strategy for solving a polynomial equation involves always starting by setting one side equal to 0, again because I talked about the emphasis of the zero factor property in the last video, but that's always a crucial component in order for the factoring strategy to work. And it says note that if either side is pre-factored and not equal to 0, you want to multiply it out, because sometimes you might encounter a situation where you have a couple polynomials on both sides that you always want to put all that stuff on one side and make it 0, if that is the case. Step 2 is to then factor the other side. As we talked about for the last few class lectures, use whatever factoring techniques you need. It might be magic X, it might be difference of squares, it might be grouping, whatever it takes, factor the other side. Then, once we've fully factorized that polynomial, we can set each factor equal to 0 and solve them just as we did above, where once it's factored, the answers just come right out, makes it way easier. And that optional last step is to make sure that it works by plugging it back in, as we did right here. We made sure that our factored answers worked. So let's do a few examples. So starting with this one, here I see it's already set equal to 0, so step 1 is check is done. Step 2 is to factor the other side completely, so there we have it. Well, we have a pretty basic trinomial here. We could always use the magic X method or synthetic division method, whatever you prefer. But I got negative 63 on top, 2 on bottom. And I'm going to need a positive and a negative here because the top is a negative. And I would then think about how can I multiply to make 63? So that could be 3 times 21. Those numbers are way too far apart. So then I might think 7. And you could always use your calculator. Like if you're not really sure how to factor the numbers completely, you could always do something like 63 divided by 7 to get 9. And so again, I could conclude 7 and 9. That will actually work, right? Because 7 times 9 is 63. And then negative 7 plus 9 do add up to 2. And again, the 9 would need to be positive because those need to add up to be a positive, not a negative. And since the leading coefficient is 1, I can take the shortcut here and I would literally have my factorized answer from the left. And then once I've factored it, I'm not done yet either, because step 3 is to actually solve the equation, right? I factored it, but the solution comes directly from this because, well, I'd set the first factor equal to 0, and 7 is the 0 of x minus 7. And for not x plus 9, negative 9 is the 0 of x plus 9. So I find the 0 of each factor. That gives me the answers to my quadratic equation. Should always be the opposite sign from here. But it's not directly from the magic X. That's something you want to be careful about. And again, I could always check those out to make sure they work. And I'll leave that for you to try by yourself. So moving on to a couple other examples, with something like this, it looks very similar, but the key problem here is that it's not set to 0 first. So you could either subtract the p squared over to the right side or subtract these over to the left side. Usually I would recommend keeping your square term positive, meaning I'm going to subtract the other 2 to the left-hand side. But either way will work just fine. And once I've done that, I can use the magic X method to factor. So I'm going to put AC on top, B on bottom, and I'm looking for numbers that multiply to negative 24 and add to negative 5. So 8 and 3 would be my first guess. That seems good. Negative 8, positive 3. And yeah, that makes sense because those add. The larger one would need to be negative to add up to a negative. And so again, I would get my direct factorization here because there's no leading term. Make sure to use p instead of x just because this given quadratic equation was p and not x, but it doesn't matter if we use x or p or q or whatever variable. It works the same no matter what the variable is. And then, of course, we solve it by setting each equal to 0, which is the same but opposite sign. P is equal to 8 and p is equal to minus 3. And we could check it out. 8 squared is 64. 5 times 8, 40 plus 24 is also 64. 8 works. negative 3 will give us 9. And over here, negative 15 plus 24 is also 9. Checks out. Looking at the next one, I would want to start by setting it equal to 0, which would involve subtracting the 53x to the other side. I would probably recommend just moving this one, again, to keep the square term positive. I would also, it's also recommended to write it in the proper order, or what's sometimes called the standard order for polynomials, where it's listed in decreasing degree, just because it's more helpful to think about them in the same way that we would every other example we've done. And again, proceed factoring. So as our general factoring strategy suggests, before I look for the magic x here, I might think about, is there a GCF to which I could use to make this a little bit easier? And here 24 consists of 6 times 4, 28 is 7 times 4. So those only share 4, and 53 is odd, so it has no common factors of 4. So it appears as though there actually is no GCF. So unfortunately, if I'm going to solve this one's quite difficult. I'm going to actually have to do 28 times 24, put that on top, which is 672, and negative 53 is going to go on bottom. So this is a little bit of a more challenging magic x because the numbers are really big. But it's good to get into a tougher one just for, because you might see these numbers and just freak out and say, okay, I don't even know what to do when they're this big. But another trick that you can do is, like the strategy I've been focusing on, is focus on how do I multiply to make 672? What are those different ways? And a way that you can actually do this is, if you check what are the factors of 672, obviously people have figured them all out before, but you can just go on the internet and see all of the factor pairs of 672. And from there, you could then look for, well, do any of those add up to negative 53? Because again, in order to add up to make a positive, these two would both need to be negative. So they need to be the same sign, meaning that when I'm adding these up, they need to add up to negative 53. So I'm looking for basically a factor pair of 672 that add up to 53. And in this list right here, I can see they've all done them in terms of pairs of 2. And I would just be looking for 2 that make 53. Actually, and I've found it right here. It looks like 21 times 32 adds up to 53. And this one's really hard because there are literally about 20 combinations for potential solutions. So this is kind of a nice way to figure this out. Rather than, obviously you could guess and check and guess and check and guess and check. You build factor trees in order to figure it out, but it would take quite a while probably to find those in general. And of course, since this one does have a leading coefficient, I need to use the split and grouping technique that I talked about in a couple other videos. So to continue, I would need to split up the middle term here. And then factor by grouping. And in the first group, I have a common factor of 7x, which should leave me with 4x minus 3. And in the second group, also another thing that I emphasized before, but in class, but I don't think I mentioned in the other video when I was talking about factoring by grouping, is anytime that there's a negative between your two groups, you always must factor that out. But noticing that when I factor out the GCF from my first factor, I'm left with 4x minus 3. Remember that must always be the same here as well. And the only way to factor and get 4x minus 3 from here is if I were to factor out a negative. And in this case, it appears as though we should factor out negative 8 in order to make this work. Right, because negative 8 times 4 is negative 32, and negative 8 times negative 3 is positive 24. So my point here was, when there's a negative in between your two groups, you're always going to need to factor out a negative, and that's something that's not necessarily obvious, because negative is not a commonality between them, so that's not obvious. And then now I can finish my grouping and I will have finished factoring. But this one was quite hard. But once I've solved the factorization, we're good to go, because my zeros come directly from there. And remember, the shortcut is you would always take the second number divided by the first number in each of those, and again change the sign as always to get the zeros of each of those factors and get the two solutions to my equation. So this one came down to fractions. It was quite a bit harder, and we could check those out, but if we apply all of our factoring techniques, we should be able to solve these. Again, if we are patient enough and keep working on them. So this is an example. This one's a bit hard. I probably would not put this on an exam just because of the scale of the numbers, because what's more important to me is that you know the strategy and the technique. But you can, my point here is that you can apply these same strategies to any problem, and again, if it has a solution, you will be able to figure it out. It just might take some more work.